Okay, let's start. So this is lecture 13. Today we'll talk about a perceptron. We'll finish up the perceptron from last time. We'll discuss two consequences of perceptron for IID data. And then we'll discuss the bias variance trade-offs. So let me remind you, the perceptron is the following most basic algorithm you can imagine. It operates on a sequence of data, x1, y1 through xt, yt. And at every time step, it looks at the new data point together with the label. It creates a prediction y hat t. And then if this prediction is correct, then it doesn't do anything. But if it's incorrect, the sign is not correct, then it does the update. Okay. We define the margin. The margin is the maximum over a direction w star, minimum over data points of yi times the projection of xi onto w star. And we take a maximum with 0. Last time I wrote it as a parenthesis plus. Here I'm just writing it with this wedge notation that's also a max. So the way to think about the margin is that you have a point xt. W star is a unit direction. That's the best direction you can find that separates the data. When you consider an xt, w star times xt is just a length of the projection onto the w star. And just assume that everything lives on the sphere for the purposes of the picture. And then we're asking that this is gamma, right? That's at least gamma. So the smallest distance among all the points, that defines the margin in the data. Is that clear? Any questions about that? Any questions about what the margin is? Yes?
Is that why you're not normalizing Gaussian?
That's right. So we have to decide the units of distance. And the way that we're going to do it is by only looking at w star of unit length. If I, what is margin, right? It's this distance between the points and these points, right? So we need to decide, are we measuring it in kilometers or meters or centimeters? And that's our way of fixing a scale. And indeed, you're correct that if we were to take a maximum over w star of length 10, the meaning of the margin would change as 1 over that number, right? So the margin and the length of the w star go hand in hand or opposite to each other. In particular, maximizing the margin is equivalent in a certain sense that we can define to searching for a minimum norm separator. Okay. Maximizing the margin is the same as searching for a minimum norm separator. Yep. Yes, that's correct. So we'll do that in just a second. Yeah. I want to keep as few variables right now as possible, but essentially, if you put here a d, then you will have d squared over gamma squared. Okay. Actually, let's just do it here, since you asked. So let this be d. Then this is going to be d squared over gamma squared. Okay. That's the more general setting. Okay, observe that the method doesn't know what gamma is, it doesn't know what d is, it just looks at the data, does the update. There is no parameters to tune, okay? Okay, so just a very quick proof to show you that this result is really simple. So here is a proof. So assume the number of mistakes over the t iterations. The number of mistakes is m. Okay, so you fix the sequence, you run this algorithm on the sequence, and you've made m mistakes. Then what can we say? So on any round t where a mistake was made,
How do you define a mistake?
that here we make a prediction, and if it's not the actual label, that's a mistake. Right? So
After updating the W, that mistake might go away.
it might not. That's correct. Yeah, there is no guarantee that it will go away. But all I'm saying is just record any round on which there was a mistake. And suppose that there are m of them. We want to show that m is at most d squared over gamma squared. Okay?
But is there, shouldn't we be concerned about mistakes becoming not mistakes and not mistakes becoming mistakes?
Yeah, so I'm going to define a mistake for this purpose as just that we're here. This is the mistake. Let me define it like that. And for instance, if you're worried,
Updates.
number of updates, that's right. Corrections or mistakes, right. In fact, I can cycle through the data, which is what we're going to do as one of the consequences until there's no more mistakes. So I could be doing that. Okay, so on any round t where a mistake was made, what we have is the following. The norm of wt plus 1 is, let's do squared, is norm of wt plus yt xt, because the update was performed. So if on round t there was a mistake, wt plus 1 is now of this form, so I'm just substituting. And now I'm going to open up wt squared plus 2 yt. Yt is a scalar, xt is a vector, right? So what I have is yt times wt xt plus the norm of xt squared, right? Because yt is plus or minus 1. Okay? Now, this number is less than 0 because the sign of wtxt was different from the sign of yt. That's why we made a mistake. So if the sign of this is different from the sign of that, the product has to be negative, okay? Or non-positive. And this is bounded by, let's say 1, and I'll leave it for the homework to replace it with a d. It's a simple exercise, okay? So what you have is that the norm of wt plus 1 squared is no more than the norm of wt squared plus 1. So anytime there is a mistake, the norm of the vector wt grows, the square of the norm grows at most by 1. Okay? So after m mistakes, this is our final vector after the presentation of t data points, is no more than what? M. Why? Because we started from a 0 vector, and every time there is a mistake, it gets possibly longer by at most 1 in terms of the square. Okay. Okay, on the other hand, we know that there exists a W star. So W star is going to be that one that achieves the maximum. Okay, W star is the one that achieves the maximum there. So there, for that W star, just by definition, it's on any data point, the margin is at least gamma, right? That's this picture. Okay, regardless of whether there was a mistake or whether there was no mistake, right? That's always true. Okay, but let me bring the yt inside and write ytxt as just the difference between the wt plus 1 and wt, right? Because there was a mistake. So that's equal to W star and WT plus 1 minus WT, right? I just brought the YT inside, and Y times YT XT is exactly the update from WT up to WT plus 1, assuming there was a mistake on that round. So anytime there was a mistake between WT and WT plus 1, or on the round on round T, this angle is at least gamma. Right? Okay. But this is at most. So there's a rule that you probably learned, that the inner product is upper bounded by the Euclidean norm of W star times the Euclidean norm of this one. So Euclidean norm of W star times the Euclidean norm of WT plus 1 minus. Oh no, I shouldn't be doing that. Sorry. Just a second. Let me now telescope. Let me add them up over all the rounds. So I'm going to add this inequality over all the rounds when there was a mistake. So I get m times gamma is upper bounded by W star times. Okay, so I get a bunch of WT plus 1 minus WT, WT minus WT minus 1, and so forth. Now they all telescope. Yeah? That's something you can check offline. They all telescope, you get WT minus W1. But W1 is 0. We started from 0. And now we're going to use the fact that this is upper bounded by the norm of W star times the norm of WT. Okay? Is that okay? So remember, the important part was that when we're telescoping, the W's don't change if there is no mistake, and when there is a mistake, they do change, and then we get this gamma. So we get m times gamma. Question? So it's important that we have this chain. They don't change, then there is an update. When there is a mistake, then they don't change. Okay. Now, the norm of W star is 1. So we just need to create an upper bound for the norm of WT, and that we have. That's a square root of m. I just take a square root of both sides, square root of m. That's it. So divide both sides by square root of m. Divide both sides by gamma. We get 1 over square root of n. Square root of m upper bounded by 1 over gamma, or square both sides. M is upper bounded by 1 over gamma squared. Okay, so that's assuming that the norm is bounded by 1. If the norm is bounded by d, you get d squared over gamma squared. Okay? It's a simple, very simple proof. So you see it's 3 lines. Maybe it shouldn't be called a theorem. It's a proposition or observation. Yes?
Is it possible to say anything about when you expect these mistakes to happen? Like the arrival time?
So this result, remarkably, works for an arbitrary sequence. That's why it's amazing. It works for an arbitrary sequence. You have no assumptions about the generative process, so you cannot say anything. But let me show you 2 consequences of this result for IID data, and then maybe we can come back to this question. Other questions? Yes.
So I still have a problem with the notion. Like, why are we interested in the number of updates rather than how the final W, how many mistakes the final W?
Great question. That's what I will do next. Okay. Yes.
So if we didn't have an update on some stage, so WT is 1 of WT, does it mean that gamma is 0?
No. It's coming from the updates are coming from the algorithm. So the algorithm has no knowledge of gamma or anything.
No, I'm just talking about the second.
Yeah. This is only on the yeah. So only when mistake.
But wouldn't prevent it from
No, because WT plus 1 stays the same, or WT stays the same when there is no mistake. So think of adding this over all the rounds and then adding a vacuous 0 on the rounds when you don't have a mistake. Then those terms will telescope, right? So on the round, so you're correct, I should have written when there is no mistake, 0 is equal to W star and WT minus WT plus 1 minus WT. That's right. Okay, we're good? Okay. Let me write this in a slightly different notation for any sequence of xt, x1, y1, xt, yt. And now I'm gonna let this live in RD cross plus minus 1. Okay, so each x is not constrained in any way. The sum t from 1 to capital T, an indicator that there is a mistake, y hat t not equal to yt, okay, where this is defined, where y hat t, just to remind you, y hat t is defined as the sine of wt xt. Sum of these indicators is no more than d squared over gamma squared, where d is really a sequence, a function of x1, y1, xn, yn, right? It's a function. It's the diameter of the axis. In fact, it's just the function of the axis. So let me not write the y's. x1 up to xn, and gamma is really a gamma of x1, y1, xn, t. Sorry for a typo. xt, yt. Okay. Okay, so this is the result. For any sequence of data, there is an algorithm, namely Perceptron, such that this result holds. Okay. Okay, consequence number 1. So now suppose x1, y1, x, I'm going to now say n, yn, are IID from some distribution P. After all, this is the setting we're interested in, right? So the question is, what happens when you run Perceptron on IID data? This result holds for arbitrary data. What happens when you run it for IID data? So what I'm going to do is I'm going to take t to be equal to n, and I'm going to do one pass through the data. Do one pass through the data. So now the question is, as you're alluding to, if I want to do well on future data, what should I do? How can I, with this knowledge, with the knowledge that for any sequence it makes no more than that many mistakes, can I extract something useful that would tell me on future data it is going to do well, right? That's the problem of statistical learning, right? If these data are coming from the distribution, they're somehow representative. So I expect that on a new data point, I'm going to do well. But that's not so clear at this point yet.
Well, I mean, you just like pretend you have an extra data point, just variables, just like get a +1 factor off.
That's right. So roughly kind of the sense of this is that I'm going to run on these data. Now, the kind of it could be that I made no mistakes on that data. And then when I get one more data point, well, this theorem still doesn't tell me that I wouldn't be making a mistake on that data, right? So it's still possible. So I need to do something else because I need to use the fact that there's a representative, right? And that analysis doesn't quite use it. So my claim is that if I take a WT at random from either W1 up to Wn uniformly at random, I pick one of these hyperplanes in expectation that they will do well. Okay? So claim a hyperplane W tau, where tau is uniform on 1 up to n. Okay? So I run Perceptron, and then I look back at all the W's, and I pick one uniformly at random. In expectation, we'll have out of sample error at most expectation. So I'm going to put 1 over n. There are several ways of writing it. I'm going to write it like this: d squared over gamma squared, where this is the expectation over the data set. And I'm going to ask, what is the expected ratio of the diameter of in the data set versus the margin in the data set, right? So remember, I should be putting hats on all these quantities. D is a function of the x's. Gamma is a function of x's and y's. According to that, that's the gamma, right? That's the definition of the gamma. And this is my claim.
So this expectation is not over B?
What is B?
P.
P. Yes, that's right. Over the data set drawn from, this is from data set drawn from P to the n, right? So it's n copies, independent copies. Each data point is according to P, and I'm going to denote my data set as S. So let's say S. S is my data set, right? So that's in expectation over the draw of the data set.
That's assuming.
So kind of, let me simplify this. Let's just assume that data live inside of a bowl. So all your cats and dogs are in the bowl. And cats and dogs are separated by 0.1 margin in that sense, right? So the problem is somewhat simple, right? All the cats are here, all the dogs are here. Then if you run a perceptron and you pick a hyperplane at random, I would expect that it will make no more than essentially 1 over n mistakes. The expected error is roughly 1 over n. The probability that it would make a mistake is 1 over n. Okay. Okay, so let me.
It's not clear to me because when you take the sample, usually you say the sum of something, and when you take the solution, regardless of the sample counts, you say expectation. So when you say expectation over a given sample, it's not.
On average over the given sample, what the quantity is. So how about this? Suppose d is equal to 1, so data lives in a sphere, and distribution p has margin gamma, right? So that means that there's a no man's land, gamma to the left, gamma to the right, and there is no x's that will ever come in this margin, okay? Then this is just this number of mistakes, the probability of a mistake is just 1 over n times 1 over gamma squared. So there is no expectation, nothing, okay? So maybe this is a bit easier to interpret. I'll just take it max with 0, and then I'm going to be dividing by infinity. That's a max with 0. That wedge with 0. Mm-hmm. Yeah. Good. Yes? That's correct. That's correct. So I'm being slightly vague. Well, this one doesn't depend on our, but the left-hand side that I didn't write down, I will do in a second. That will have an expectation over the tau. That's right. Okay, so let me do the proof of this fact. The proof is very simple. I'm going to, that orange box, let me just write it slightly differently. 1 over, now t is equal to n, right? So I'm going to do this. 1 over n. I'm going to divide both sides by n. Indicator. Let me plug in that y hat. Y hat is wt times xt, the sign of that, right? So another way to write this is that yt times wtxt is less than 0, right? Then I make a mistake, right? That's the same way, that's the same statement as saying the sign of this is different from yt, that the product of them is less than 0, right? Just another way of writing it. Right, so I haven't changed anything. So we know that this is less than d squared over gamma squared. And now I'm going to take an expectation on both sides. But in fact, before I do that, let me do the following. This is nothing but an expectation with respect to a choice of tau, right? Another way of writing it is expectation with respect to tau of indicator y tau, w tau, x tau less than 0 is less than d squared over gamma squared. Right? That's just the definition of a uniform distribution.
But that's when n is large, right? Or
Anything. I mean, the definition of tau is that it's uniform, so it has 1 over n weight.
Yes.
Yeah. Okay. And now let me take an expectation over the data now. So I'm going to take expectation of both sides. Because now this is a random quantity. Remember, it's still random in the data. Right? Yes?
Should there be 1 over n?
Oh, 1 over n. Thank you. Thank you. Times 1 over n. Times 1 over n. Thank you. Right, so let's take an expectation of both sides. So now we have expected over s, expected over tau. Indicator that y tau w tau x tau is less than 0, less than this expected value of d squared over gamma squared times 1 over n. Now I'm going to exchange the two expectations, right? I can do that. So let me do it in place. You can do it in your notebook. You can write it again. So here, like that. Okay. I haven't changed anything. And now it's going to come. Now will come a kind of a tricky part. If you're very comfortable with probability, you will say, of course. And if you're less comfortable with probability, then you should go home and kind of work it out. Okay. So the part that I will now say is the following. So I can now think about conditioning on tau, right? So given tau, I have this statement, conditionally on tau, or I have this expectation, conditionally on tau. Now, w tau had not seen x tau and y tau, because w tau was computed with past data up to tau, and we never came back to the same data. So w tau had never seen x tau, y tau. Yes? And everything is independent and identically distributed. So I can just rename this y tau, x tau as xy, right? It's just a dummy variable from this point of view, right? So to do this argument carefully, you have to do the Tower law of iterated expectation, right? But so please go home and convince yourself that I can just think of putting another expectation over x, y, and writing it like that, right? I mean, if you're not uncomfortable with probability, this seems like a bit of a magic, but it takes just a few minutes to write it down carefully. Okay, you can do that at home. So let me do this. Let me at least write this. Expectation over xy pair from the same distribution P, and then expectation over the data set S, expectation over tau. Right? Okay, but what is this quantity? This quantity, in fact, I didn't even have to do this renaming. You can just see that this is L of W tau with the notation. It's the expected out of sample loss of W tau. Is the expected out of sample performance with respect to the indicator loss of this random hyperplane. Okay? Questions? Now I'm going to put a special symbol just to indicate that this L, capital L, that we've defined in the previous lecture, right, out of sample loss. I'm just going to put little 0, 1 just to indicate that this is with respect to an indicator, 0, 1, right? In particular, this is the probability of making an error. So what the statement is saying is that the probability that there is a mistake on a new sample, out of sample, by a randomly chosen hyperplane, on average, is roughly 1 over n times 1 over gamma squared. Okay.
So basically most of the steps that you're doing rely on the fact that the indicator random variable can be replaced by expectation.
Indicator cannot be replaced by expectation. The expected indicator is probability of an event. That yes, but I'm not relying on this. This could be something else. The claim that the probability is bounded by something, of course, relies on that being an indicator. I could just say expected indicator of a mistake, expected loss, right? That's this quantity, right?
And the expectation of the indicator is the probability of the event.
That's right. That's correct. That's correct. That's correct. Right. So the statement was a hyperplane W tau chosen at random after you run the perceptron. In expectation, will have out of sample error at most that. Hopefully, I convinced you of that fact. Yes? Okay. So that's one consequence of the perceptron bound, which took 3 lines to prove, but it's a very powerful result because it holds for an arbitrary sequence, and we're specializing it to a sequence of IID data. Okay. Questions about this consequence? Yes? Exactly. That's consequence number 2. We're not going to show that they should get... Okay, so I don't know if you can prove that they get better over time, but probably most of you will say, well, pick the last one, right? Pick the last one, so that should be better, right? So I cannot quite prove a result for the last one when you go once through the sequence. Maybe that's a project that one can try. Let's see, do I know how to do that? I don't think I even know how to do that right away. Okay, so what I'm going to do is I'm going to cycle through the data many times until I have no more mistakes. And then for that final guy, I will prove a good result, right? Make sense? So consequence 2, number 2, cycle through data S. So again, S is the data set until no more mistakes. Output W capital T. So what we know is that T is going to be upper bounded by what? Do we know that this will stop? Do we know that this process will stop? If I've got data which are linearly separable with some margin, I'm going to cycle through that. How many data points will I overall look at? What is T, right? So I can do once through the data. The worst thing that can happen is that I only make one correction. So I know that I will make at most 1 over gamma squared mistakes, or d squared over gamma squared mistakes, right? That's my budget. The worst thing that can happen is that I go through the data, I make 1 correction. Then I go another time through the data, I make 1 more correction, right? That's the worst thing that can happen. Because if I go through the data and I make no correction, then I'm correct on the data. I will not do anything from that point on, right? So T is at most n times d squared over gamma squared, right? That's the most that it can take. And I will see the same data points several times, right? That's important. I will be seeing same data points several times, and maybe on the first pass I don't make a correction to a data point, but then on the second pass I do a correction to that data point, right? Okay. And now I want to understand how good is this hyperplane, right? So the only thing I know about this hyperplane, well, not quite the only thing, but what I do know about this hyperplane is that it separates the data, which was not the case for W tau. W tau didn't necessarily separate the data, right? This one does, right? So think of data like all the cats being supported here and all the dogs supported here, right? And then there is no man's land here. Okay. Now I got random data, random cats, random dogs, and I do perceptron. So what I do know is that I've separated the data. I've separated the data, right? But this one separates the data, right? For instance. You see? So it could be that I'm cutting into real cats and real dogs, right? And that's going to be making mistakes, right? It's going to say that these cats are on the wrong side of the hyperplane. But hopefully the mass of this is not too big, right? So how do we quantify that? If you start working through this is going to be a nightmare. Because you will say, well, it can't be too much mass because I would have seen an example of that, right? That's the point of statistical learning, that if there is a lot of mass here, then you would have seen examples here, right? And since you didn't, there is not mass, and so you shouldn't be making too much mistake, right? But such an argument is going to be very hairy very soon, right? Very, very difficult. I'll present you a 3-line argument, or okay, maybe 6-line argument, to show that this is a good hyperplane. Okay, so here's the proof. Oh yeah, so I didn't write down the statement. So claim is that the expected L01, now I can write it like that. This is the out of sample indicator loss of WT is bounded by expected, again, d squared over gamma squared times 1 over n. This is the important part. This goes down with more and more data. Yes?
So in the previous one, you didn't have the assumption of subprobability from data.
If that quantity is 0, then the result is trivially true, right? Because you get infinity. You divide by 0. Right, so now this is going to get into a lot of little detail. What if there is a measure 0 event when you get infinity? Let me just avoid that. I mean, you could imagine, you could engineer a situation where that would happen, but let me avoid that. That's more that's a more specific question. Let me just leave it as like that. Yeah. Yes.
So this d approximately equal n times that d squared over gamma squared. Roughly, right? But maybe you need a +1 or something like that, because if every cycle has one mistake, then that would be exactly enough. Maybe you need one more.
Yeah, maybe you need one more. Yeah, we're not going to be using that, so yeah, maybe you need +1.
And is this n +1?
Yeah, that's n +1, which is a stronger statement than what I've written before. Let's do n +1. Okay. All right. So again, if you're confused by this term, just think of this as 1 over gamma squared. That's kind of the easiest way to think about this. Just forget about this expectation. Just think of this as 1 over gamma squared. What is this expectation under? What else is random? What is random? The data, right? So this is just expectation over the data. Now, in fact, well, we've discussed that this is a random quantity because it's a function of the data. Maybe I should be putting hats everywhere. Sorry. So you can think of WT as it's a function of data, right? Because it's an algorithm. So this whole thing is random in the data set, and that's the expectation. Okay.
So the benefit of this is that you eliminated the random choice, basically. Instead of saying choose a random.
That's correct, and that's right. And I'm pretty sure that this will be better than a random hyperplane, as was discussed. So the bound is the same. +1 doesn't really matter, but the bound is the same. But this one will probably do better in practice. What we can prove is this result. Okay. So proof. This is going to be a little bit more cute and a little bit more tricky. The bound is the same as before, yes. I think in practice this will separate the data, and a randomly chosen one will not probably separate the data. So my guess would be that this is better in practice.
I see it's just a bound.
This is just a bound, right? Right. Yeah.
Bound is the same, but the actual.
The actual performance, I don't know. Try running it. I mean, it's a simple coding exercise. You can do it in 5 minutes. Good.
So this is not tight in that sense.
It's not tight. Yeah, we can think later how to improve this. Let's think later. Okay, so let's do the proof. Let me just say I need to think about this. I don't want to make a statement on the spot. Okay, so a proof. So this is going to be a little bit tricky, so please stay with me. I'm going to take n plus 1 data points instead of n. I'm going to say x1, y1, xn, yn, xn plus 1, yn plus 1. Okay? Or IID. Okay? So this is just for notational convenience. Instead of out of sample on this point, on xy, I will think of out of sample on the n plus 1th point, right? It's just a naming issue. Okay, so now to simplify the notation, let me just call these z's, okay? Is that okay? I'm going to call these zn plus 1, right? Just for simplicity. And I'm going to denote L of WZ to be the indicator of Y WX less than 0, right? So this is the indicator of a mistake. If W makes a mistake on the pair XY, that's a mistake, and I'm just gonna abbreviate it by L of W comma Z, where Z is to be understood X comma Y, and W is this W. Okay? Okay. So let me do this consequence carefully. So claim Okay, so the out of sample expected L01 of WT is defined by this, right? That's the same. It's the same quantity. Now, so what is the claim? The claim is that this can be written as expectation over just to keep with my notation, S and Z n plus 1 of 1 over n plus 1 sum t from 1 to n plus 1 loss of W minus t. Let me explain what this is, ZT. Okay, so here W minus t is final hyperplane when trained on S minus a ZT plus a Z n plus 1. Okay, so let's see if this makes sense. So what is the meaning of W minus t? We leave out the teeth example from the n plus 1 data set. Now we've got n points. And we run the algorithm on those n points. And that's the W minus t. Is this point clear? So again, we got n plus 1 data points. We remove one of them. Now we've got n data points. And we run the algorithm on them, on these n points, as before. And that's the definition of W minus t. Is that okay? The definition of this W minus t is it's trained on S minus ZT, but with the Zn plus 1. That's the new data set. Except this definition is not quite correct for t equal to n plus 1, but you understand what the correct definition is, right? Yes?
So if I give it Z plus 1, does that get anything else? So you take out ZT.
Take out ZT and put in Zn plus 1. And the definition of W minus n plus 1 is just the usual data set from 1 to n.
Oh, S does Z.
That's right. Right. This is right. Right.
What is n plus 1?
So let me just a second. So this is S. This is S. And this is the new data point. Is that clear? What was the question?
I mean, the Zn plus 1 should be rotated, right? I mean, when you discard Z1, Zn plus 1 is the Z1 in the second cycle.
Let me do it graphically. So this is n plus 1 data points. I'm going to leave out 1. And now I'm going to run the algorithm many, many times until it fully converges. No more mistakes. That's my definition of W with the index, whatever I left out. Then this is all in my mind. I'm not proposing to run it. This is just for the analysis. I'm leave out this one. I run, right? Again, this is not something that you want to do. It's just for the analysis purpose. Yes?
So for the sense 1 through Z plus 1 are symmetric, right? Because
They're IID. They're IID. All right.
the summation brackets kind of feels like overkill because, because they're symmetric, we might not need to actually go through indices.
That's right. This is the claim. The claim is that what you want can be expressed just for the analysis purposes as this leave one out average. because all of them are the same. What you're suggesting is it actually doesn't matter which t you take. In expectation, they're all the same because they're all drawn IID from the same distribution. So training on this and testing on that in expectation is the same as training on this and testing on that. And it's the same as training on this and testing on that, and so forth. Does that make sense? That's the leave one out type of analysis. Another way to say is leave one out is an unbiased estimator of what we want. And just to make this connection, cross-validation is exactly this idea, right? When you leave some data out, you train on the rest and test on left out data. That's exactly cross-validation, right? Except here it's just one out, right? We're leaving one out and testing on that. And that's an unbiased estimate of what we want. That's why people do cross-validation, because in expectation, that's the right thing, right? Or at least with leave one out. Make sense? Okay. Good. So let's see. What can I erase? Maybe this. Okay. All right. Now, imagine running Perceptron on Z1 up to Zn plus 1, right? So now I'm actually going to run it on a sequence of length n plus 1. Okay? And I'm going to run it many, many, many times until I make no more mistakes, right? So cycle until no more errors. Now, we know that the algorithm will make at most gamma squared over d squared over gamma squared corrections, right? So let I1 through IM be indices of data points that were involved in a mistake on any round. In other words, I've got n plus 1 data points. I'm going to run, I make a correction. I record that index. That data point was involved in a mistake. I continue cycling through the data, and I mark any location of the data point where there was a mistake. Okay?
You can have multiplicities.
You could correct the same data point multiple times.
Are not distinct.
So these are distinct. But it could be that I1 was involved several times in the correction. Okay? Okay, now consider index T, which does not belong to the set I1 through IM. Okay, this is the cute part of the argument. Consider a data point that was actually never corrected through these cycles. There was never a mistake on this data point. Now, whether that data point was included in the data set or was not included in the data set doesn't matter. because no correction was made on this data point. That clear? So we could have left it out. And we would have gotten to the same place without that data point. Moreover, the final hyperplane correctly predicts this data point because it's not in any of those, even at the end. Which means that the number of terms which are not zero in the sum is at most m. That's the amazing proof. Right, let me do it again. I run Perceptron on n+1 data points, cycle until no more mistakes, and I mark indices of points where a mistake was made. There are at most m of them. But if you consider index t, which was not in that set I1 through IM, then whether ZT was included or was not included in the original data set doesn't matter. No correction was made ever on that. It was always predicted correctly. So this W without the T would have been the same if you included or didn't include the data point. And this is correctly predicted by this W without the T, right? So the number of non-zero entries in that sum, number of non-zero entries in this sum, I'm going to mark it as a star, is at most m, and therefore expected 0,1 loss of WT is at most, well, expected value of m. What is m? M is at most d squared over gamma squared times 1 over n+1. And the only thing here that I swept under the carpet is that this d and this gamma are defined on a sequence of n+1 data points. Really, I can write it. So d is a d of x1 through xn+1, and this gamma is a function of n+1 data points. Okay, instead of n, but it's not a big deal. Okay. This is the simplest proof of out-of-sample performance of anything that I know. Okay, just a few lines. Right. We've proved with math that if you run Perceptron on n points or n+1 points until no more mistakes, that's a good idea, because out of sample you'll also have a probability of error at most 1 over n+1, right? 1 over n. This is pretty much as well as you can hope, as good as you can hope this to be, right? 1 over n. With more data points, you get less and less probability of error. Yes?
Sorry, how's the last one?
Why? Well, it's a little bit worse, right? Because it's the it could be that you draw n points and that's the diameter, but then when you draw n+1 points, you get a slightly bigger diameter and possibly a slightly smaller margin. But that's a small difference.
So I don't understand the connection between the t. Like, I mean, you could have said if there are only m mistakes,
Yes.
I1 to IN. I mean, there could be multiplicities here, I understand. So that's the connection. Yeah, I'm a little confused between the connection of this idea that t is not in the set and you have at most m non-zeros.
Well, so all I'm saying here is, so consider running Perceptron on these data. right? And marking those indices when there is a mistake. And consider the W, which is on the same data set but left out a teeth point. If that teeth point that you left out is not in that collection, then this coincides with WT, W capital T. This coincides because whether you left it out or you didn't doesn't matter. And so what right? And then you would predict correctly on that point.
Yes, well, what does that mean? So I understand.
So that's 0 then. So the only number of non-zeros is the number of indices on which you've made a mistake on the n+1 data points. Yes?
Is it possible to do like slightly more work and get like a high probability result instead of
You should be able to do it, yes. You shouldn't be.
It's weird that this like expected value on the right-hand side might increase over time as n increases. Does that cause problems?
What increases?
Implementations over n+1.
This one?
But is it possible that like that increases with n?
Yes, so it could, but this margin, I mean, we can get rid of this, right? We can say, suppose that the distribution is not supported on this strip of gamma, right? Then this is just a deterministically, at most, 1 over gamma squared, right? And then suppose the distribution of the data is bounded, right? Only supported, okay, then this is deterministic. So we could replace, I made it a bit more general, but we could replace this with distribution-dependent quantities, not data-dependent quantities. That's a good question, yes? In general, yes. Yes, because the locations of mistakes would be different depending on how you cycle through the data. But we're fixing one. No, so this bound is, no, so on average, okay. Just for the purposes of the analysis, I'm going to fix the order and cycle through the data. Because I need to guarantee that I converge at a finite time. Otherwise, I wouldn't converge. Now, your question is, what if I permute it on a particular round? Yeah, I think you should be able to do that. Yeah, you should be able to make it a bit more careful and do the same analysis. Yeah, that's right.
So where in the proof do we see that we're cycling through the data?
It's all in our head. In reality, there is only one WT. In reality, there is only one WT, right? And it's run on n data points. We're just, from this point, we're writing it in a completely hallucinating way as we have actually n+1 data points, and let's leave one out, right? This representation just helps us.
So what is n here total?
N is your data set size. I've got n.
It's not the total number of points after cycling many times.
No, that's T.
That's T. Right.
Yes, capital T. I'm gonna leave it like that. Please go home, read the slides, and hopefully it will make more sense, or ask questions after office hours or anyway, any other medium. Okay, so let me just give you a little bit more information about the what we were doing. Okay, so the perceptron update xt plus 1, w t plus 1 is equal to wt plus yt xt can be thought of as doing a gradient step on the so-called hinge at zero loss function. So that is max of 0 and minus yt w xt. If this is so-called hinge at zero loss function, it looks like this if you plot it in terms of yt xt, sorry, yt w xt, then it looks like this. Okay, that's the hinge at zero function. And if you take a gradient, if you're on the correct side, in other words, w times xt times yt is a positive number, then there is no mistake. Then the zero kicks in, right? So if w correctly predicts yt, the sign on this xt, then you're on a zero part. You're here, and now there is no mistake. So the derivative is 0. So you make no update, right? So naturally, just by thinking of this as the gradient, that gives you this update and the do nothing update when you're correct. So you can check that the gradient of this when you do make a mistake is just ytxt, right? That's the derivative of this part with respect to w. And when you do a gradient step, you typically do wt minus the gradient, and the gradient itself is minus ytxt, and so you do the gradient step in the right in this direction, right? Make sense? So now what we've done is go once through the data. Well, in that case, every data point is a fresh data point for you. When you go once through the data, every time the data point is a fresh one. You have never seen it before. And so you can think of this one pass as stochastic gradient descent on the expected max of 0 and minus yt w xt. So you can think of what we've done in the first consequence as really doing stochastic gradient descent on this expected objective, okay? Or maybe I can erase the yt and just leave it as like that, right? Expectation over xy. All right. The second consequence, on the other hand, is doing a cycling gradient descent, full gradient descent on the full objective on the empirical objective, 1 over n sum of max 0 and minus y w yi x I from 1 to n, right? So they are doing slightly different things. Those two approaches that we've done, they are doing slightly different things. The first one is really getting fresh data at every time step, and therefore you can think of each gradient as being an unbiased gradient of this objective. For the other one, we're really a full optimization on this objective until we separate the data, until we have no more mistakes. These two represent two different paths, two different approaches that you can undertake or you can imagine. This approach has been very popular lately, especially because of a lot of data. We have a lot of data, so you can afford to go through the data once. In practice, no one goes through the data once. People go through data several times. And therefore, in practice, we do something in between. If you go 3 times through the data, you do something in between. But we have very limited understanding. There are some recent papers. We have limited understanding of what happens in between, because you start introducing dependencies. You cannot treat it as this problem, but also it's not fully this problem. Okay, so again, this approach has been popular in the last decade or so. This is the approach that Vapnik and Chervonenkis advocated in the 60s, and that's where machine learning started to develop by understanding what can you say about minimizer of an empirical risk. And what we've done today is analysis of an empirical risk minimizer. We've minimized this risk to 0, and we've analyzed out of sample performance, even though we've minimized an empirical objective, right? Yes. That's right. So we're not really doing full gradient descent.
And we are not also doing even stochastic gradient descent.
We're not doing stochastic. We're doing cyclic gradient descent. So we're cycling through the data. That's another version of this gradient descent. You could imagine full gradient descent where you take all gradients at the same time and go to the minimum. That will also separate the data. But it's going to be hard to analyze that one.
Even like in this particular case, we know that it's nothing zero training. But in general, that's not clear. It's definitely cycling.
If you assume that data are separable, then cycle gradient descent will get you to the minimum by the analysis that we've done.
I mean, we should just show it in this particular case for this.
That's right. That's right. That's right. So the rest of the, well, I don't want to say the rest of the course, but the next 10 lectures is essentially trying to understand what can you say about, more generally, about methods that minimize empirical objective. In some sense, we got really lucky that with just 5 lines, we're able to analyze the minimizer of this objective. There's something very special about this case. In general, it's going to be a little bit more intricate. I will provide techniques and tools that you need to analyze minima of empirical loss and how they do out of sample. We've done the most basic example you can imagine. And the proof is very simple and cute once you kind of understand it. Okay, thanks a lot. I'll see you on Thursday.